So welcome to the pre-recording of lecture 19 of MCS 572. So it's lecture 19, but it is our fourth lecture on GPU computing. So I started lecture 16 with an introduction why one should consider GPU acceleration, mainly for increased bandwidth and for compute-bound problems for teraflop. In the second lecture, the compute unified device architecture was explained, how one could run graphics processing units either in graphics mode or in device mode, suitable for floating point computations. And in the previous lecture, I introduced PyCUDA and also CUDA.jl to define programs that are accelerated by GPUs. So as you can see from the structure in this lecture, I will go back to the tutorials for the CUDA in Julia, because they are actually, Julia has an advantage in the sense that advantage over Python. When we were using PyCUDA, we actually did need to understand C code. Here actually Julia solves this two-language problem. So you can define kernels and also how you launch them in Julia itself. But the main point of this lecture is actually that defining a GPU accelerated program is not that hard. There are a couple of steps that one needs to follow. I think I can explain it in a 5-step process. So, what is the running example? What is the main example for this lecture? Well, I will consider the computation of a square root, but then the square root of many numbers. So in some sense it's a little bit strange in the sense that I cannot directly think about why one would want to compute the square root of a huge array of numbers. However, it could be a prototype of a complex root finder, where every thread would start an iterative process somewhere in a domain. So it's not that far-fetched. In the first project we examined Muller's method for root finding to compute the basins of attraction. Compute the Mandelbrot set is very similar also here. So it's a little bit a simpler example than the Mandelbrot set. Okay, so every thread will run 5 iterations with Newton's method on complex numbers. So it is relevant for scientific computing. It's also relevant to illustrate the data parallelism. It's very straightforward, one-dimensional. Every thread will do the same function, but then on different data. Okay, so this is a hands-on lecture, so we will be using NVIDIA GPUs. Every NVIDIA GPU has a compute capability. Here are the main numbers listed. So it's represented by a version number as x.y. Currently with Pascal we are at 6.0, so this introduced the atomic addition on 64-bit floats. But to me, the most important feature, and actually all the GPUs that I had that I used actually had already double precision floating point operations capability. So the 1.3 was, in my opinion, the milestone. Okay, this is a crowded slide. If you have an account on a computer with the software development kit of CUDA installed, then you can do a device query. So here is this device query. This is compiled, so this comes with the CUDA installation. So here you see that we are using the driver version 11, which is not the most recent one, and Pascal has the compute capability 6.0. You see the number of CUDA cores that are available, the number of multiprocessors, the number of cores per multiprocessor. The clock rate of the memory, still expressed in megahertz. And we will in later lectures examine what the limitations mean for the number of registers, the maximum number of threads, also the memory that we have available. So the warp size is 32. Okay, so we can also run a bandwidth test. So this is also provided as the first utilities in the software development kit. And I should actually say that learning CUDA, it's actually a good recommendation that I would have is to look into the examples that are provided in the software development kit. Okay, here you see the results of this bandwidth test. So we go from host to device, from device to host, and then also from device to device. The theoretical peak performance in the bandwidth was 700 megabytes per second. Here you see that we get, as far as the bytes per second goes, I don't think we are actually going to 700. There is the keyword pinned. That means that the memory is paginated. So the operating system divides the memory into pages, and pinned means that the pages are fixed. We can, as a programmer, define which pages needs to be fixed. This could be beneficial if there has to be done a lot of memory transfer between device and host. Okay, so it's easy to get lost in all kinds of technical details, but here is the 5-step process to get our GPU code running. We write a C and C++ program and label our functions with these predefined keywords: device, global, or host. This allows us to indicate which functions that will be executed on the host, on the CPU. In some sense, that's the default. If you leave it off, then the compiler will assume that it will run on the host. Global is are functions that are launched on the CPU, executed on the GPU. Device functions are functions that are called on the GPU. These are in some sense directives for the compiler. So we can also specify which compiler should compile the code for the host. So there is the final step that we can specify this when we compile with the NVIDIA C++ compiler. Okay, as a programmer, we have to be aware of the data parallelism, which thread will work on what element in the array. We have to make sure that we have data that is available on the host and on the device. So in some sense, we have every variable split it off in twice. We have a device and a host variable. And then the functions that will be launched are called kernels. So they are the ones which will be prefixed by this underscore underscore global underscore underscore. Okay, step one. So here you see examples of the host, device, and global. The default is underscore underscore host underscore underscore. So if you leave it off, I don't think it matters. In particular, I only use either global or device. So it's possible to define an entire library of functions that will be used on the device. These functions are typically stored in a file with the extension .cu. The main program can have the extension CPP as C++, but if everything needs to be compiled by the NVIDIA compiler, then for this example here, we will have the .cu files. Okay, global are the ones that will be executed on the device but are called by the host. So it's important that this is accelerated computing. So the CPU still is responsible for a lot of work. So in some sense, it's never quite honest to compare accelerated code with only the CPU. So the CPU is always active. Okay, so then there is the mapping of the data on an array. So we will launch a grid of blocks, and every block will have a number of threads. So if we work, say, with an array of 1024, then we can work with 32 thread blocks, each of 32 threads. So every thread has a unique identification number that is composed of the thread index, so the thread index within a block, and then the number of the block in which it resides. So you see the formula here to compute the unique thread identification number, and that thread identification number typically is used also to access the data. So the code that is here on the slide shows a template for a typical one-dimensional thread organization. So we have a .x. In the previous lecture we showed that you could also have a .y. But to keep it simple here, we will do a .x. So we can, within the program, we can query the thread index, the block index, and then the size of each block. The block dim gives us the number of threads that are inside a block. So we have the input and the output arrays. So they are in global memory of the device. And then we have the function that is called. And when we call the function, we can specify inside the main program the dimensions. So how many blocks of threads do we have? How many threads in each block? Typically it's the other way around. So you decide first on the length of the array, and then you decide how to partition it. With GPU acceleration, we often start out with, say, 32 by 32. So in some sense, it's Gustafson's law. We have to select our problems large enough in order to make sense, in order to give the GPU sufficient work. Okay, so then there is what we called in the previous lecture the boilerplate code. So we have to allocate explicitly here the memory on the host. So I will use complex variables, call them CUDA double complex. CUDA, by the way, has the data type double 2, which is convenient to store the real and the imaginary part of every complex number. So we have the X host and the X device. So the star in front of them means that the X host is the address of the first number in the array. So we compute the size, and you see we do the CUDA malloc to allocate space on the device. So these are instructions that are defined by the program that will run. So the NVIDIA compiler will decide what instruction gets executed either by the host or the device. And then there is the memory transfer from the host to the device. We have to indicate the number of bytes, and we also have to give this keyword CUDA memcopy host to device. So we typically read the CUDA memcopy from right to left, first specifying if we go from host to device or from device to host, and the number of bytes. Then we copy from host to device. So what gets changed is the first argument in this CUDA memcopy. Going to the last statement. So here I have omitted the code that does the computation. So we can also, when the result is called y, we copy then after the computation, we copy from the device to the host. The same number of bytes here. So in our square root, we have double complex numbers on input, double complex numbers on output. The syntax of the CUDA malloc is a little bit strange, but it's not so strange if you are used to C working with this void. We are essentially allocating blocks of bytes, contiguous blocks of bytes. Okay. Then we have the kernel, which is the square root. So the kernel will be executed on the device, but it will be launched by the host. So every thread will essentially execute this function. So you see inside this function we have the thread identification number, which is the little I, which will be used also to get the data. What is here very nice is that threads are executed in warps, so 32 threads, and they will read adjacent information from these arrays. So we will call this later memory coalescing. So it's very nice worked out here for this example. In order to see the speed up, we will have a frequency parameter. So it's in some sense this square root is not compute intensive enough to matter here, but imagine an iterative root finder. We do it multiple times in the program. So you see how the square root is launched. So f is the frequency, that is what the user can specify. We determine the number of threads per block, so w is kind of suggestive that it would be at least 32. The n better than also be a multiple of 32. So we specify the number of blocks and the number of threads per block. With this, so we have the square root function, which has 3 arguments, the dimension, and then the input data, the output data. But then before we have the parameters of the run, so the tuning parameters, and this is done with this triple less than and a triple larger than. Triple because there is the double, and you don't want to confuse. So there is the double less than from the insert operation of the output, and also the output operator in C++. Okay, step 4 already. We are actually almost there. Step 5 is the compilation with the NVIDIA C++ compiler. So we can specify which compiler should be used. So I tested this on Pascal, so this is Linux. I also did this on a Windows laptop. Perhaps I should also have specified the makefile here for Windows. There you can use the Visual Studio command line version of the compiler that needs to be used for the CC bin. So what the nvcc does, so you see that the file has the extension .cu. The nvcc is going to separate the code that will be executed on the device. It will be separated from the code that will run on the host. So if you are familiar with C and C++, and in some sense in this course this is still the first official programming language, then there is not that much more that you will need to do. So let's now look at the code for the complex numbers. So there is the CUDA double complex that is here defined to be mapped onto the double 2. So the double 2 is a native CUDA type. So the real and the imaginary part, if you would define it in a struct, in a C struct, then that's possible, but you would not have the nice alignment. The alternative is to work with 2 double arrays. One double array that stores all the real parts and another array that stores all the imaginary parts, the corresponding imaginary parts. That would then require that every thread does 2 reads and also does 2 writes. But that would still be very good for memory coalescing, which means that adjacent threads, threads with adjacent thread identification in one block, they read and write, they do reads and write memory accesses to adjacent locations in memory. So the double 2 will help us to do this. Okay, so here the host generates random complex numbers. So using the sine and the cosine from the mathematical libraries. Then the device runs the square root. So there is a square root of the math functions. When I compiled this most recently, there was a warning that actually the math functions are somehow a derived include and they should not be directly included, but this may be deprecated in a future release of CUDA, so it still works for now. So here you see the square root that we are applying. So in some sense this is device. So the keyword here is the underscore device underscore. This is a function that will be executed by the device. It's also called by the device. And it returns the radius of a complex number. Then the host does the output. Here you see the overloading of the operator to output a complex number. So the real and imaginary part, and we will plot, we will print everything with 16 decimal places. This is mainly for checking. Okay, so we define complex addition, complex multiplication, complex division. So these are the device functions that are defined. So, and the nice thing is that I said that we were going to use C, but we do operator overloading in C++. So we can then in the code write the plus. Here you see it. So this is the kernel function. So global now means again that this is launched from the host but executed by each thread. And we were running 5 steps of Newton's method. And what is critical here is that we are using the thread index to access the read from the input that is stored into a register. So the I and C, the increment, the C and the R, and they are double twos. So you see here that if we are going to compute how much registers that we're going to use, we are going to use for the double two, these are two doubles essentially. So we have already 6 doubles, and if you are running this with 1024 threads, you are already using 6000 registers. So there are these scalability limits. So sometimes an instruction cannot be scheduled because too many registers are already in use. It's important that we actually separate the reading from the writing. So in some sense, this is instruction level parallelism. In the for loop, it would not be a good practice to keep on working with the, so you could say I'm going to save a register. Instead of working with R, I'm going to work with the ith entry of Y. But this would actually imply that every thread would always read and write from the global memory, which is pretty bad. So here what happens is that registers are being used. More instructions actually mean that there is more instruction level parallelism. So this is important. One can see how many operations that are here being executed. So these are complex additions, complex divisions. What is the number of computations per byte? So we have the memory intensity that we defined earlier in the course, but we will come back to that also later. All right. Then in the main program, to make this a user-friendly program, if the user runs this for the very first time, most likely will not know what the arguments are. So we have the dimension, the block size, the frequency, and then a 0, 1 flag to indicate if we're going to do this for testing or not. So in order to avoid overflow, I should probably have pointed this out, we will work with random complex numbers with radius 1. So the numerical stability is kind of important here as well. Okay, so in some sense, doing the square root can actually be then defined simply with the polar representation also. This could be an extra check on whether this really works. Okay, so here we have everything together. So we have the transfer of the data, the launching of the kernel, and then the copying from the data from the device to the host. So the frequency here makes that if you are doing only one square root, then most likely the memory transfers will dominate the entire computation. So the time that it takes to run this will actually be dominated by the memory transfers. So that's why there is this frequency to do a little bit more computations per memory transfer. Okay, so here you see the test. If the last parameter was 1, then it will pick one random index and test whether the squaring of the original of the output compares agrees with the input number. So if you take the square of the square root, you should have the original number back. So this is the test. All right. It seems still, if you have not followed the evolution of the graphics processing units, it still seems a little bit strange. You could also say, why keep this unified device architecture? Well, this model actually scales very well. So we have to decide when we run the program on the number of threads per block and on the number of blocks that we are running. So here you see a multi-threaded program with 8 blocks. If we have 2 cores or if we have 4 cores, we can simply adapt these specifications. So it is a model that scales quite well. Okay, so here are the runs. So this is the test on the correctness. So you see that except for somehow the last 2 decimal places, this gets printed with 16 decimal places, that it all agrees. So typically another way to compare correctness is to have the host do also some computation. So sometimes one sees a slight difference in the round off, but that could also be because the order in which things are executed on the device and on the host is different. Here I've run this on Pascal with 64,000, array of 64,000, 32 threads per block, and doing this 10,000 times with one last check at the very end. And you see that the wall clock time was 300 milliseconds and the system time is 200 milliseconds. So there are timings one can actually time the spent by the kernels, but here I took just the wall clock timer, and you can see here how active how much of the time, so 200 time, was spent on the system. This also incorporates the device, but it also includes the memory allocations and such things like that. But still, one can play with, so 32 threads per block is kind of a minimum. But you see that it changes, the execution time actually changes a little bit if you increase, if you change the number of threads per block. It does not change that much. The user time is the time that the CPU works. So you kind of can see in the total wall clock time the portion of the device, how much the device helps with the acceleration. Okay, that was C and C++. Let's now go to the Julia code. So I was lucky that there is excellent documentation, tutorial documentation. The problem that we are going to consider is different from the square root. We're going to consider the addition of 2 vectors. So a little bit more extensive than what we did in the last lecture. In the last lecture, I picked just the very first kernel. This is a third kernel here, where I will indicate, I will show how one can also control the number of threads and the number of blocks. So the number of threads per block. So the number of threads equals the size of our problem. So here we work with blocks of size 256. And in this picture that I took from the Julia CUDA tutorial, which was taken from the suggestive title, An Even Easier Introduction to CUDA. It could be that if you look at that technical blog, it's even easier than what I explained. You see the assignment of the work. We have 4096 blocks, and every block has 256. So you can probably guess that the total dimension is 1 million, 2 to the power 20 to be precise. So thread with identification number 3 inside the block with identification number 2 is mapped. So we compute the previous block. We have the block index 2 multiplied with the size of the block and added to the thread number of that thread number in the block. So that means that in that block, the thread with identification number 3 will work on number 515. That's kind of, again, the template on how threads are mapped to data. Now we don't do C and C++, we do plain Julia. So this is a Julia function. So we compute this formula, the index. Julia starts at 1, so also the block index actually starts at 1. So array starts at 1 here, so this is why you have the -1. So I still find that this is not too good. So there is the stride that gets computed from the grid dimension with the block dimension. So it could be that every thread does just one number, but it could also be that it does more. There is the acrawl inbounds. We actually had this also last time, and I didn't explain it. So this means that the array checking is not done. So typically, Julia comes with the checking of the indices, whether the I is actually really a valid index in the array. That is necessary to generate good error messages in case something is wrong, but this slows down the performance. So this is why the acrawl inbounds is there to say to the compiler, look, we know what we're doing, don't check whether the I is inside. Okay, that's the Julia code, the Julia function that will be executed. In the main program, we will define 1 million numbers. X is 1, Y is 2, and we would see 3. So that's what the test does. The test will test all the entries, and it should be printed test passed. The importance of this slide is that you can see that we can specify the number of blocks and also the number of threads per block. So the assignments, or the what comes after the acrawl CUDA specifies that we will launch the GPU_add3. We will launch it with a number of blocks, which is these 1 million 2 to the power 20 divided by 256. So the division is by default an integer, is by default a floating point number. We take the closest, largest integer with the seal. Okay, and that's it. So if we want to do a vector addition, in Julia we just have to think about the mapping of the thread identification number onto the data. So we have to specify what we will be running, and of course be mindful of this thing that the arrays in Julia, they all start at 1. Okay, but other than that, it's surprisingly much simpler than, so you don't need to worry about the data transfers. So this is what is taken care of. You do have to specify how they are filled. So in some sense, this you would have this array that exists already of the vector, the data structure that exists already in Julia on the host. Then you would need to still work, if you have an x underscore h or x host as we did, you would still need to define the corresponding x underscore d or x underscore device. Okay, so here I just copied this from the tutorial. If you, and as the exercise will show, you will probably have to dig a little bit deeper if you want to translate the complex root finder, the square root computation onto Julia. Okay, but there is an even easier blog, an even easier introduction, which I got from the technical blog from Mark Harris via the CUDA Julia tutorial. So I wasn't aware of that, so it keeps on getting easier. So you don't really need to read the entire CUDA programming guide, but you're more than welcome to do that. So we will go through several aspects of the best practices guide and the programming guide when we look at the matrix multiplication problem. So I did not cover PyCUDA in this lecture, but that's one of the exercises. Now, if you were to, so here are the exercises here. So the exercise 3 with PyCUDA, it might be even easier here because we have already the C code. So with PyCUDA, you actually still have the two language problem. PyCUDA takes care of the boilerplate code that you can define. You can work with NumPy arrays, but you would still need to define the C code. And actually, as I'm talking about this now, I'm actually not entirely sure that if it would be so trivial to do the complex arithmetic, how you would do that. Okay, but the square roots example with Julia as an added exercise. Then the topics 1 and 2, the exercises invite you to play with the posted code. One could actually define a root finder. So if you have a polynomial of very large degree, Newton's method is only local, so you could start at random numbers, and you would see that starting at different random numbers, you would actually find different regions of the complex plane. You would actually find simultaneously many roots. And then you can essentially divide out the roots and make a new polynomial. So this could actually be a data parallel root finder, which in each step might be possible to find almost quite quickly the number of roots of a polynomial, all the roots of a polynomial. So the second step is kind of could also lead into a project. Okay, so in 44 minutes I have explained what I wanted to explain. I hope that programming in CUDA is not that hard, corresponding to the statement that I started in the first lecture, lecture 16 on GPU acceleration. If you are familiar with the parallel way of thinking with MPI and or with OpenMP, then GPU acceleration is not that hard if you keep in mind the evolution of the device architecture.